This chart maps the 12 fundamental fermions of the Standard Model. From bottom to top, the data shows that their observed masses span 12 full orders of magnitude. The top quark is so heavy it decays before it can form a hadron, while the neutrino is so light we can only measure the differences between its mass states. The Higgs mechanism mathematically explains how these particles acquire mass through interaction with a background field. However, the mechanism provides no rule for why they acquire these specific values. Today, these masses are treated as empirical free parameters, measured in colliders and plugged into equations as fixed inputs. Mode identity theory offers a deterministic alternative, treating these constants as derived outputs of spectral geometry. Understanding the distribution of these 12 orders of magnitude requires mapping the topological constraints that determine the identity of a particle. The derivation takes place on a specific manifold, the Poincare homology sphere. This is a topological space with a finite fundamental group, and its underlying geometric skeleton is the icosahedron. This shape is mathematically described by the binary icosahedral group, known as 2I. In this framework, particle mass and identity emerge from the stabilizer subgroups of this group. We can trace the quantum properties observed in high-energy physics back to distinct geometric components, specifically deriving color charge, the spin domain, and weak isospin. Every Platonic solid has three defining elements. The icosahedron has faces governed by a threefold rotational symmetry, edges governed by a fourfold symmetry, and vertices governed by a fivefold symmetry. These three geometric symmetries determine the particle's complete quantum identity before a single numerical mass parameter is calculated. This is the master mass formula. It calculates the mass of a fermion using four specific factors. Each of these components traces independently back to a single topological postulate, the embedding of a Möbius strip into the three-sphere. The first factor establishes the baseline scale. It is the fourth root of the cosmological constant energy density, creating a vacuum energy floor of 2.25 milli-electron volts. At the other end of the equation is the vacuum-twisted Reidemeister torsion. When we take the tensor product of a particle's representation with one of three isolated vacua, this torsion term provides the fine structure variances within each mass shell. Every single fermion mass in the universe represents a scaled geometric perturbation of the cosmological constant's vacuum energy. The triangles forming the faces of the icosahedron possess a rotational symmetry of order 3, which isolates the Z3 stabilizer subgroup. Restricting any irreducible representation of our group to this Z3 stabilizer forces a rigid mathematical decomposition. This decomposition sorts the states into two distinct categories: color singlets, which correspond to leptons, and triplet or anti-triplet pairs, which correspond to quarks. The representation known as R7 provides a clear test case. When restricted to the face stabilizer, it produces exactly one singlet with 0 colored pairs, matching the properties of the electron. Color charge emerges as the physical expression of icosahedral face geometry. Next, the focus shifts to the edges. These are governed by the Z4 stabilizer, representing an order 4 symmetry. This decomposition forces an exact binary. Integer spin states map to real Z4 content, resulting in a geometric domain size of 60. Half-integer spin states carry only complex pairs, requiring a double domain size of 120. This domain size determines how we evaluate the constant phase exponents in the mass formula, mapping where each representation sits on the finite spectrum. The edge structure of the geometric domain hard-codes the spin statistics connection, separating bosons from fermions. Finally, the vertices, governed by the Z5 stabilizer, map to the extended E8 Dynkin diagram via the McKay correspondence. Here, representations act as connected nodes. A node's distance from the trivial origin mathematically acts as an elevator. Each step further out on the graph increases the mass shell by an order of magnitude. This distance determines the magnitude of the mass shell, scaling it by the square root of the cosmological hierarchy. To assign weak isospin, the geometry passes each state through the Coxeter-Galois gate, a two-stage filter evaluating parity. Under the first rule, any state entering the spectrum through an integer bosonic channel evaluates to a lower weak isospin, -1/2. The second rule evaluates Galois conjugation. Completely Galois-fixed tensor products retain upper isospin, +1/2, by structural inertia, the precise mechanism defining the identity of the top quark. Generational mass hierarchy and weak isospin are both explicit functions of a representation's distance and parity on the E8 graph. Evaluating 8 representations across 3 isolated vacua yields 24 precise mass predictions, ranked here against empirical standard model data. The structural filters we established assign 10 of the 12 standard model fermions to these exact coordinates. 9 of those assigned particles land within a factor of 3 of their observed mass. The precision peaks at the electron, the up quark, and the muon. The pure geometric predictions for these 3 particles fall within 6% of measured values. At rank 15, the geometry generates a single mass shell between the muon and strange quark. Due to the phase stabilizer, it splits into a singlet sector for the muon and a triplet color sector for the quark, 2 particles occupying the same mass shell. The model hits fundamental constants through deterministic geometric intersections. We must address the structural tensions in the results. There are unassigned gaps, including the charm quark, which is currently displaced because the weak isospin filter assigns rank 17 to the tau lepton. There is also tension at rank 14, where the down quark has a 3.22 ratio gap, potentially indicating the need for an R8 Galois correction. A second neutrino mass gap exists between our first 2 ranks. Experimental bounds require this unassigned mass to sit between 10 and 50 millielectron volts. These anomalies define exactly how the theory can be falsified. The formula generates 6 entries populating the electron volt to kiloelectron volt dead zone. At rank 16, the theory makes an explicit, testable prediction, an undiscovered state at exactly 349 megaelectron volts. A mathematically rigorous theory must provide a roadmap for its own validation on testable grounds. There is a final proof involving the weak force. The dodecahedral geometry underlying this space has an angular defect of pi/5 at each vertex. When this passes through the non-oriental boundary of the Möbius strip, the holonomy halves that defect to pi/10. The cosine of pi/10 yields a highly specific geometric projection factor. This factor exclusively corrects the weak coupling constant to within 0.4% of its measured value. The weak interaction is the only standard model force that violates parity, matching its unique traversal of this non-oriental topological twist. By contrast, the strong force's color charge transmits through the oriental faces of the geometry, reaching the observer without acquiring the twist projection. The mass spectrum, quantum identities, and interaction couplings follow directly from the properties of the Poincare homology